Alrighty, folks. So we had just started talking about transformation of functions. I'm glad our little definition is showing up. It wasn't showing up last time. So I do actually want to talk a little bit about what kind of transformations we are going to see. So let me write this down. Okay. So we actually started looking at that plus k when we did example 1 last time. So what I want you to note with that plus k is that if k is a positive value, then your graph will move upward, okay? If k is a negative value, your graph is going to move downwards. Okay. Oh, I'm just showing you that example or that equation right at the beginning here, how these transformations work. So this is what we had looked at last time, right? We did that x plus 3, I believe. Now this h value, this is actually going to work like circles did. So if you have x minus h, that means h itself is a positive number. So if you see x minus 3, that means 3 is a positive number. And if h is a positive number, your graph actually moves to the right. If h is a negative number, your graph will move left, which means your parentheses here is going to have a plus sign. So when h is positive, you will actually see x minus h, or whatever that number h will be. But if h is negative, that parentheses ends up becoming a positive. So you will have x plus 3. That means 3 itself is a negative number. So for the h value or the horizontal translation, you always go with the opposite sign. This a value here, if you actually have a negative sign on a, you are actually going to see a reflection of your graph with respect to the x-axis, which means with respect to the x-axis, it reflects. If a value is greater than 1, so it will be like a number 2, 3, whatever, anything greater than 1, your graph will stretch. If a value is between 0 and 1, so basically if you see a fraction in there, your graph will shrink. These are basically all the different types of transformations we are going to be talking about. We started with vertical translation, which was this upward and downward movement. Then we are going to be looking at horizontal translation, moving your graph left and right. And then we'll get into reflection and then stretching and shrinking. And like order of operations where we do, please excuse my dear Aunt Sally, we actually have an order when you have multiple of these transformations within the same equation. You actually have to follow an order of how you do the transformations, because obviously we want everybody to get a standard answer, a standard graph. So this is where we started last time. We looked at vertical translation, right? Our main graph was f of x equals x, and then we did x plus 3, which means all of these units moved up by 3 units. And I guess I did the graph on our different page. I don't have the graph here. So we had looked at vertical translation last time. Now we're going to look at vertical translation, but going down. So this is our next example here. Y equals x squared as our base function, and then you've got y equals x squared minus 3. So even for the x squared function, you can use your -2, -1, 0, 1, and 2. So you can use those standard 5 points for x squared, and then we'll do x squared minus 3 on the other side. Okay, so what kind of points are you looking at for the x square function? What are those y values going to be? So you should not have any negative signs left because the idea, yeah, because when you're doing -2 squared, that means you're doing -2 times -2. So the two negatives will become positive. So all answers will be positive. So 4, 1, 0, 1, and 4, right? So all four of those, sorry, all of those values. Okay.
I got a question.
Sure.
On my calculator, if I was to put in -2 squared, it still shows a negative.
So put -2 in parentheses before you do the square. So it's because you're not doing the parentheses, it's actually treating the negative as an individual sign. It's only squaring 2 times 2, and then it's leaving that negative, so you get -4. Yeah. Yeah, those negative signs will get you, so be careful about that. Now I'm actually going to use the same 5 points for my second function, x squared minus 3, but obviously your y values are going to change because it's a different function. So go ahead, calculate those. Again, remember when you're calculating, you will still do -2 in parentheses, then square it, and then -3. Do you have those values?
I do.
Yeah, what do you got?
I got 1, -2, -3, -2, and 1.
Yeah, so again, you will see those values repeating for -2 and +2. So you're basically taking the y values that you already have in the first function and you're literally just subtracting 3 from them. So from each of these y values, you're subtracting 3, and that's going to give you this column right here. Yeah, so you will have 1, -2, -3, -2, and 1 and 1. Okay? All right, let's look at the graph for this guy. It is a parabola, very good. Okay. And what happened with the second parabola?
It moves over.
Okay, so you've got 0, 0, 1, 1, 2, and 4, -1, 1, -2, -4. That will be for the original function, y equals x squared. Now make sure you are labeling your graph so you know which graph represents which equation. So this one here is our standard, y equals x squared. And then we've got 0, -3, 1, -2, -1, -2, and then we had 1. Every single y value has been subtracted by 3. So basically, as Jacob mentioned, if you start with that origin, you can see it has moved 3 units down. Every single point on this graph has now moved 3 units down. So that's your downward translation or your vertical translation going down. Okay. All right, so let's talk about, again, domain and range for the main function and domain and range for the second function. So for the y equals x squared, which is the graph in red, what's our domain and range? Oh, yeah, because those arms will keep going, right? Very good. So domain will be negative to positive infinity. Range, the y values. Very good. Yep, starting at 0, including 0. So that's bracket 0 going to positive infinity because your graph will be going upwards. Very nice. All right, now for the x squared minus 3 function.
The domain is the same, but the range is -3.
Instead of 0. Yeah, so your domain will still stay the same because both your arms are going to go towards negative infinity and positive infinity on the x-axis. So domain did not change. But since our graph moved downwards 3 units, your range will be affected. So instead of starting at 0, this is very good, starting at -3. Yeah. So like I was telling you last time, that sometimes domain and range does not get affected, but sometimes it can, and that just depends on the kind of function you have. So that's why we're going to try and remember doing this for all of our functions so we get in the habit of recognizing domain and range. Everybody okay on this example? Any questions? No? Okay. Okay, so remember how I was telling you that every time you make one change on your function, you are creating a new member of the family. So what happened with these examples here, and I think we had, yeah, so this was a linear function, f of x equals x and x plus 3, but this guy here is from the square family. So basically by putting that -3 at the end, you've created a new member. So every little transformation, even if you put just a negative sign in front of x squared, creates a new member of the family. Okay, so now we're getting into horizontal translation, which means your graph will be moving left or right. So this is where you have to go with the opposite sign. So that means if you have x minus 3, that means 3 itself is a positive number and your graph is moving to the right. If the number itself is going to be negative, that's what we should have, I think, in our next example. Yeah. So if the number itself is negative, you will actually have a plus sign. So that tells me my graph has to move left. So for horizontal translation only, if it's negative, move to the right. If it's positive, move to the left because you're going with opposite signs. Because the idea here is when you have square root of x plus 9, that means you have x minus -9. So h itself is a negative number and you move left. But they're not going to write it as two negatives. They are going to give you x plus 9. So this means h is negative. Your graph is moving left. Here, in this example, your h is positive. Your graph is moving to the right. So for the x squared, again, I'm going to use those same 5 points. -1, -2, or -2, -1, 0, 1, and 2, which will give us obviously the same y values, 4, 1, 0, 1, and 4. And now we're moving our graph to the right. I'm actually going to start out with the same points, but I'm actually going to show you that we're going to need more points than this. Okay? So let's see what we come up with so you kind of have an idea of why we need to add more points. So go ahead and calculate. This guy here is x squared. This one here is the x minus 3 quantity squared. So go ahead and calculate your values for the second thing. Are you done with all of these, Alexander? Because I'm seeing some kind of graphs on your paper. So for -2, what will be your y value?
4,
25.
25, 16.
1.
Oh, well, we're on the other one, sorry. 25?
25. Because you are going to be doing
3 to the right.
3 to the right. Yeah, so well, you're going to have -2 minus 3 squared, which will become -5 squared, which becomes positive 25. Because you're putting in -2 for the x, right? So -2 minus 3, and then square that whole thing. So in that same way, you would be doing -1 minus 3, which is -4 squared, and -4 squared would be 16. What did you say for 0?
9.
9? Because you would be doing -3 squared for 1,
Four.
4, and for 2. Whoa. Okay. So again, if we try to graph this, no, that's not what I wanted. Okay. Okay, so again, our base function is y equals x squared. Bless you. And now for the second one, the x minus 3, you had -2 at 25. So that's going to be beyond the scope of our function, right? Same thing with -1 and 16. We won't be able to graph it because we just have a 10 by 10 grid, which means you're actually starting out at 0, 9, 1, 4. So 0, do I have 9? 1, 2, 3, 4, 5, 6, 7. Not really. What? Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9 will be somewhere over there. And then I had 1, 4, 2, 1. Okay, very good. So that's actually what's happening. Out of the usable points, we've got only 3 points and they're all on one side. So we actually need to get more of that parabola. And that's why the points that we started out with are not going to be enough.
You just, once you have the first parabola and you know that it moves through to the right, you just take each point and move to the right.
Basically, very good. That's exactly what you are doing. Taking each point from the original function and moving it 3 units to the right. Yeah, very good. So basically what's happening is, like in the previous example where we subtracted 3 from our y values of the base function to get this column, for this function, what we're actually going to end up doing is to the x values, add 3. So all of these original x values, technically we should have added 3 to it. So that would be -2 plus 3, which would be at 1, -1 plus 3, which is at 2. And you will notice these are the same y values. So again, if I take 0 plus 3, that would be 3. 1 plus 3 would be 4. 2 plus 3 would be 5. And then these points here would translate as the same, 0, 1, and 4. So your usable points, and I don't know if this guy lets me change colors, but your usable points for us here are actually going to be this 5, but technically you can also use that 0, 9 because you can graph it on paper. So we need 3, 0, 4, 1, and 5, 4. So that's 3, 0, 4, 1, and 5, 4. And this should give you your transformation function. And I think, Brittany, you had asked me last time, like, how do we come up with these points for our x and y values? So that's basically, with each function, then again, you kind of have to decide. So since our function was moving to the right, 3, which means all your x values were being added by 3. Okay. Questions on this one? All right, so again, your x squared function would be the same domain and range as we saw in the previous example. So tell me for our transformation function, x minus 3 squared, what is your domain and range going to be now that we've moved it 3 units to the right? Same thing, it doesn't change? Because we didn't move our graph up or down, right? So since the graph didn't move up or down, your range actually does not change. You're still starting at 0 and you're still going to positive infinity. Now, as far as the domain goes, we did move our graph 3 units, but you know, these arms were still going to positive and negative infinity. So even though we moved it 3 units to the right, it didn't change the fact that you are still going to positive and negative infinity. So yeah, very good. Domain and range will actually end up staying the same for this. Are we okay? Question? Okay, so take a second and think about what acceptable values can we use for number 4, y equals square root of x.
All positive.
And very good. So square root, because again, we don't want to deal with that whole imaginary number thing. You can start at 0 for all positive values. So let's start at 0. What's the next number I can use? Before 2. Yeah. Now, when I take square root of 2, will I get a nice and clean answer? Okay, so what would be a next easy? 4? What else? 9, yeah. Now, technically, you can use 16 next, but you're not going to get it within your graph, right? Because 16, we won't be able to graph it. So that would be our next clean number to use. So square root of 0 is 0. Square root of 1, 1. Square root of 4, and square root of 9. Very good. So remember how we talked about this is technically a negative 9, which means our graph is moving 9 units to the left. So how will that change our x value?
You're just going to subtract 9.
Same thing that we did in the previous example. We added 3 there. Here, you're going to be subtracting 9. So 0 minus 9, negative 9. 1 minus 9, negative 8. 4 minus 9. Negative 5, right? Because your 9 is a larger number, which has a negative, and then 9 minus 9. 0. All right. I mean, you can use 16 here, but you know, when we graph it on our grid, you won't be able to plot that point. But yeah, I mean, you can definitely use 16. And actually, if you did 16 minus 9, what would you have? Alrighty, so now tell me what those y values will be for our second function. Now you are doing negative 9 plus 9 on the inside, which will give you 0. Negative 8 plus 9. Very nice. So what will those other numbers be? Negative 5 plus 9. Zero plus 9. Very good. And then 7 plus 9. All right, so in this case, we subtracted 9 from all our x values, and you should notice that your y column is the same as the base example, right? The base function. Okay, so let's go ahead and graph this guy. Okay, let's do our grid. Okay, so we need 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, again, I'm starting with my base function. So that was at 0, 0, 1, 1, square root of 4 was 2, square root of 9 was 3. And we did this graph last time in section, what was it, 3.1? No, 2.2. I'm lost. 2.2, I think. So that's just the upper part of the parabola opening on its side. And now when we do minus 9, which means you're moving 9 units to the left, you're going to be starting at negative 9, 0, negative 8, 1, negative 8, 1. What else did we have? Negative 5, 2, 0, 3, negative 5, 2, 0, 3, 7, 4. Somewhere over there. And that 7 over 4 is technically your 16 and 4 ordered pair from the original, which we can't really graph on this function. You should be starting out at 7 units for the one. Get square root.
I was like, there's something wrong.
Yeah, because you still have the square root, right, on your function?
Yeah.
Did everybody get that? We still working through it? Okay, what does our function look like? We put arrows in that because you're going to keep continuing in that direction. Let me see your function. Okay, looks good, I'm here. Good, looks good. Destination graphic notes.
I was like, why is it going?
Alrighty, let's talk about domain and range for the original square root of x function. So for the square root of x, which is in red, what can we comment on the domain? Yeah, because you don't have function on the left-hand side of your graph, which means there are no negative x values, and we know we cannot have any negative x because of imaginary numbers. So you are starting at 0, going to infinity. Very good. What about the range, the y value? Same thing, very nice. Starting at 0 and going to infinity because again, there is no graph on the negative y-axis side of our function. All right, now what happens in the transformation function where we moved our graph to the left?
the domain would be -9
To
to infinity.
yeah, so it's same thing like we had seen with that range for the second example. Since we moved our graph 9 units to the left, your domain will now start at -9 to infinity. Very nice. And range would not change. You're still going from 0 to infinity because you haven't moved your graph up or down, so that range has not changed. Does that make sense? Questions?
So
Mhm.
on the red one,
Yes.
since it does get all the way at -9, I wouldn't put a name.
So on the red one,
I'm
You-
sorry, the black.
the black one. So yeah, you are starting at
Oh,
-9.
never mind.
So that's up there. Yeah, sorry, it's in the wrong location.
Lazy.
So yeah, you are starting at -9 to infinity, but range does not change. Question on that? Okay, I will take that as you are doing really well. Okay. Okay, so we've looked at vertical translation, we've looked at horizontal translation. Now this is where we're getting into reflection. So as it's telling you, it's basically creating a mirror image of your graph with respect to the x-axis. So if your graph is above the x-axis, it gets reflected below the x-axis and vice versa. So all you really have to do to get that reflection is if you have positive y values in the original function, they will all become negative. If you have negative, they will all become positive. So basically the idea is change the sign on your y coordinate and you get the new coordinates for your reflection function. So again, here we're looking at a linear function, y equals x, y equals -x. So let's go ahead and use those, again, 5 basic points. And since it's y equals x, what will your y coordinates be? Sorry? No, it will be the same because this is the original y equals x function. So -2 will be -2, -1, 0, 1, and 2. Now for the transformation, the reflection part, which is y equals -x, this is where you're going to change your signs. Yeah, very good. So same 5 points for the x value. But now you are doing negative of -2, which will actually make it positive. Negative of -1, which will be +1. 0 does not really take a negative sign. So 0 will stay 0, and then you're doing -1 and -2. So this is what happens in reflection. Your negatives become positives, and your positives become negatives. And then, of course, your graph will also reflect that. So let's go ahead and graph this guy. Yeah, it's going to be straight lines. Okay, so our original function was at 0, 0, 1, 1, 2, 2, -1, -2. So y equals x. Now basically, remember the idea is you're doing a reflection with respect to the x-axis, which means this upper half of your graph is going to get reflected down here, and this lower half of your graph is going to get reflected up here. And those points that you came up with for your table should show you that. So this guy will go down here. These points will go here. Like I said, this upper arm is getting reflected down here. The lower arm is getting reflected up here. For the original function, y equals x, what's your domain and range?
Infinity to infinity.
For domain range,
Domain.
domain, negative to positive infinity, okay? Range? Range will also be negative infinity to positive infinity, very good. And then for the reflection function, y equals negative x. Yeah, because even though you did a reflection, domain and range really did not change. And that's because these guys are straight lines. Right now, if it was a parabola, you would see a difference, but with straight lines, it really didn't affect that. Any questions at this point? All right, people, dazzle me with number 6. Let me see what you come up with. So it's the same square root of x function that we did in example 4. So you can go back and use those same table values for the first part and then do the negative square root of x for the second part. Okay, so you've got 0, 1, 4, 9, and we can't really graph the 16, but we can put it in there. X values will stay the same no matter what. It's only the y values that will become negatives for the positives. Alrighty, so we'll do our base function for 0, 1, 1, 4, 2, 9, and 3. And then we'll do the reflection. So starting at 0, 0 again, but now it's 1, negative 1, 4, negative 2, and 9, negative 3. Just a mirror image in the x-axis. Okay, so we just did the original function, so the domain for that was 0 to infinity. Range was also 0 to infinity. How will that change for our negative square root of x?
Your domain stays the same,
Very good, 0 to infinity.
and then your range is going to be 0 to negative infinity.
Okay, so put that smaller number first, so which
All right.
means negative infinity should go first.
Right.
But yeah, your numbers are correct. So we're starting at negative infinity and basically think of it as stopping at 0 since you cannot go further up. So you're basically coming from negative infinity and stopping.
Why wouldn't the domain be negative infinity?
Oh, domain, because those are x values, right? So you're
Oh, yeah,
still
yeah,
starting
yeah,
at
right.
0 and going to the right. So that's why the domain doesn't get affected. And see, that's kind of what I wanted to imply here is each function is going to be so different, right? Because they're not all going to behave in the same way. So you just kind of have to think of what numbers I can use and then what my graph looks like. Very good. All right. Yes. The range
Why the negative infinity?
Because when you did the reflection, this guy was going up to positive infinity,
Oh,
right?
right.
But now this guy is going down. You know, as he goes right, he's going to keep going down.
Right.
Which means he's now headed to negative infinity. That's why. So range will change, but domain does not.
So why does it matter if the zero after or before?
Because we always write interval notation with the smaller number first,
Oh, okay.
and negative infinity would be smaller than 0. That's why. Okay, very good. Anybody else? Anything popping up? Good. All right. So all of these transformations that we have done so far have been non-rigid. Sorry, rigid. Yes, rigid. Sorry, let me say that one more time. All the transformations we have done so far have been rigid, which means the shape of our graph did not change, right? We just basically picked it up, moved it up or down, left and right, or we reflected it. But the next set that we're going to look into is your stretching and shrinking. That means it's actually going to stretch and shrink your graph. So those are non-rigid transformations, which means the shape will be affected for your graph. Before we get into the stretching and shrinking, I do want to look at this paragraph here. So remember how I was telling you the order of your transformations is really important, like we do with order of operations, because now here they're talking about if you take your x square function, which is your parabola, reflect it in the x-axis, which means you're putting a negative on it, and then translate it 1 unit up, your function is actually going to end up looking like this because we did the reflection first and then moved our graph 1 unit above that. Now they're saying if we change that order and we actually move our graph 1 unit up first and then do a reflection, your graph is actually going to be like this, where you have x squared plus 1 in the parentheses. And since we did the reflection last, you're going to get negative on the outside. If I distribute that negative sign, it ends up becoming negative x squared minus 1. So look at the difference between those two equations. You did the same movements, but you did it in different order. That means you're actually going to end up getting two different functions. And if you actually look at their graphs, and let me show that to you quickly here. Okay, so if we did that first one, which was negative x, oh, no, not you guys, there we go. Negative x squared plus 1. Okay, so that's what this looks like because you reflected first and then moved it, right? If I remove that plus 1, that's just my reflection, right? So instead of opening up, your parabola is opening down. But when I do plus 1, it's going to take the same graph and just move it 1 unit upwards. But with the other function that we were talking about, that guy was negative on the outside. And then in parentheses, we had x squared plus u. Where are you? X squared plus 1. So this is where you actually moved it 1 unit up. So if I actually take that negative sign in the front out, you took your x squared function, which would start at 0, 0, and you moved it 1 unit up. And then we decided, okay, we also want to reflect it. So it was now at 1, which is on its reflection is going to be at negative 1. So you can see, because we do the transformation in different order, we don't get the exact same graph. And that's the reason why once we're done talking about stretching and shrinking, we are actually going to talk about what order you do these transformations in. So this was just something quickly to show you what those two graphs end up looking like. Okay, so remember, for the stretch to happen, that a value in front of your graph has to be a number larger than 1. For the shrinking to happen, the a value has to be between 0 and 1. And if you slap a negative sign on that, that's when you get the reflection. Okay, so just stretching and shrinking itself does not have a negative sign. The negative only comes when you're doing a reflection. So you can see in this one, we're actually including all three graphs in here. So you've got your base function, which is x squared. And then you've got the 1/4 x squared. So since that 1/4 is a value between 0 and 1, we should see shrinking happening. And then 4x squared, the number 4 is greater than 1. That's where you should see the stretch happen. Okay, so we're actually going to graph all three of them on the same coordinate plane. So let's start out again with our basic x squared function values. So that's our -2, -1, 0, 1, and 2. Okay, so that's going to be your 4, 1, 0, 1, and 4. For the second one, let's do 1/4 x squared. If you use the same x values, and the last one would be 4x squared, again keeping the same x value. So go ahead and calculate those last two tables and let me see what y values you're coming up with. You've already calculated the x squared here in the first table, right? Which means you're just taking these values and multiplying it by 1/4 to get this table, and multiplying the same values by 4 to get the last table.
So we multiply it by 1/4 and then we.
For the two different functions, yeah. So you will be doing basically here, because our x squared is going to be 4, right? And you're taking that 4 and multiplying it by 1/4. So 4 times 1/4? 1. Okay, very good. And then you are doing 1/4 times 1. So what's 1/4 times 1? 1/4. So these guys here will actually be 1/4 and 1/4. 1/4 times 0. 0. So you've actually got 3 good points in there, because that 1/4 will be harder to graph, but we do have 3 good points that we can use in there. You sure?
Yeah.
Yeah? Okay. Same exact thing for the last table. You're going to be taking 4 and multiplying it by -2 squared, which is basically 4 times 4. And 4 times 4? 16. So you're actually going to have 16 for the top and bottom. 4 times -1 squared? 4. And again, 4 times 0? Okay, so again, you've got 3 good points that you can use in there, because that 16 again will be out of the bound of our graph. Okay, so make sure you've got your tables completed, and then I'll go ahead and show you the graphs for these. So this is number 7. Base function is x squared. Shrinking is 1/4 x squared. Stretching is 4x squared. That is 4 and 4, okay. That's weird.
It's like a little.
Are you doing the 1/4 right now?
Yes.
Yes, he will be a little odd looking. Okay, so again, in red, I am doing my base function. Again, make sure you are labeling all of your graphs. That's our base function-ish. Okay. And then 1/4 was going to be, let's see, -2, 1, and 2, 1. So -2, 1, 2, 1, and you had 0, 0. The other are quarters, so I'm actually not going to do those points, but this should give us an idea for a shape. So in green, I have the shrunken graph, the 1/4 x squared. And then we've got a stretch, which is -1/4 and 1/4. So -1/4, +1/4, 0, 0. And in black, we have the 4x squared. So basically, think about a rubber band. What happens when you stretch a rubber band, right? It's going to get really narrow as you stretch it out. So that's actually what's happening with the 4x squared. So sometimes, with shrinking and stretching, for the stretching part, you can also think about your graph becoming narrower. And then with the shrinking part, very nice, it's going to become wider. Sometimes it might help of thinking in terms of narrow and wide. Straight line is probably going to be the most nondescript in the sense that it's just going to be the slope that'll change, right? You're not really going to be seeing a shrinking or stretching happening. And I'll actually show you this graph on our Desmos calculator here, but let's talk about the domain and range for these functions before we leave this page here. So let's do the original function. That's your y equals x squared. We've already talked about that before. Your domain is negative to positive infinity. Range is 0 to infinity. Now let's talk about the 1/4 x squared function. 1/4 x squared, which is the green function. What's happening to your domain and range? Yeah, because you're not really moving your graph left and right, which in this case wouldn't make a difference. You're not moving it up or down. You're literally just changing the shape of your graph, so it does not affect your domain and range. Very nice. And what about the graph in black, which is y equals 4x squared? Same thing, very nice. Everybody okay on that part? All right, let me see your graphs, people. Good, looks good. Looks good, looks good. The red one looks more like a V. On the exam, I'd take your points off. He looks good, he looks good. Lloyd, you still working on yours?
Yeah.
Looks good.
Yours looks like a V too.
Does it? Mike? Don't make fun of my graph. He
There's
says, "Mom, he just looks skinny."
Yeah, on the test you can that too.
Make fun of my graph. Justin, are you still graphing? Okay. All righty. Do not make fun of my graph. I'll take it. All right, let's do our base function. So that's the x squared. Then we did 1/4. This is Desmos. Give me a second. Do you see that link right there? Desmos.com. It's just an online graphing tool.
like midway.
Do you have an app for it? I'm sure there's an app for it. There's an app for everything. Is there an app? Has anybody ever used the Desmo's app? You have? Okay, yeah, so Justin confirms it. There's an app for it. So if you have space, which my phone has absolutely no space, but if you have space on your calculator, download on your phone, you can download it. But so that you can kind of see how the green function was our base function, and then when we did that 1/4 in front of x squared, it widens it out, right? And the idea is if you change that denominator of 4, I don't know, let's make it 16. Look how wider that gets, right? Because of that 16, it's making it flatten out even more. So that's kind of the idea with that shrinking, sorry. And then we had 4x squared, which, as you were making fun of my graph, kind of looks straight-ish. Okay, I take back my comment of yours looking like a V. Okay, and again, just to show you with that 16, look how skinnier that gets. So the higher those A values will get, the more stretch you will see. So we were at 4. So again, green is your base function to make a comparison.
You give us something on the test that is to the, like, 1/16 expected ease.
Yeah, that would be hard to graph because, you know, if you're dividing by 16, those numbers become really small. So normally we try not to do that, but then, you know, sometimes my MATLAB is generating those numbers on its own, and you can kind of see some funky stuff showing up in there. Yeah, because it just depends on what they have programmed in there for values, but hopefully nothing too ugly. Okay. All right, guys. So that's our stretching and shrinking. So here they're actually just talking about, you know, how your ordered pairs would change comparing from the base function to the shrunken function. And you can actually look at these values on those tables that we did for each of the 3 functions. So if you go back to that table that we just worked on, this is kind of what they're talking about. Originally, that ordered pair was -1, 1. But then when we did the shrink, it became -1, but now a 1/4, right? And then with the stretch, the -1, 1 will become 1/4. So basically all of those ordered pairs, especially these in the middle, is where you're going to see the change. And then of course, with these +2 and -2, you will also see those numbers changing because of that stretching and shrinking. So that's basically what they're talking about here in this little paragraph. But now we're getting into multiple transformations. So we've done each one of these transformations individually, you know, as a single transformation, but what happens if you put it all together? So look at that order. You always start with the horizontal translation first, which means moving your graph left and right. Then these are all at the same level. So if you have a reflection, and you know, you either have a stretch or a shrink, you're not going to have both in the same graph. So reflection and stretching and shrinking at the same level. And the very last transformation you do is your vertical translation. So start with horizontal, then reflection, stretch or shrink at the same level, and then the very last one is vertical translation. So you actually have an example here. So let's see if we can talk about it.
Why did they give us 5?
Oh, I did that to show you each step as you go about following that order.
Oh, okay.
So what does the negative sign tell us in front of that 1/2? What kind of transformation does the negative give us? Nope, not the reflection. That's what I was looking for. That negative means we are going to have a reflection in our graph. The 1/2 is what transformation? Very nice. That's going to be shrinking. Alrighty. The +2. Because it's plus, right? Which means you go with the opposite sign. So it means H is -2. You are moving left. And the +4. Very good. That means K is 4 and you are going up. Okay. So you've actually got pretty much everything that we could possibly squish in there. You've got reflection, you've got horizontal, vertical movement, you've also got your shrinking, right? And like I said, you can't have stretch or shrink together. Now this is going to be the crucial part when you are doing these multiple transformations. If I take the negative sign away, if I take the 1/2 away, if I take the 4 and the 2 away, what's my base function?
Square root of x.
Very nice. So you have to identify what your base function is, which is the square root of x. So that's going to be our starting point. And since it's square root of x, you cannot have negative x values in there, which means these guys are again those good positive numbers that we can use for square root of x. So go ahead, get your y values down. So 0, 1, 2, 3, and 4, which we won't really be able to use that last table. Okay, so order of transformations. You first start with horizontal translation, right? Which means, and since I don't have room to write it here, I'm going to write my y value down here. Horizontal translation is going to be square root of x plus 2, right? Is this 2 makes our graph move to the left. So how will this table change for us if we're moving our graph to the left?
So you have the same y values.
Same y values, and
Everything would be 0, -2.
very nice. All the x values you will now subtract by 2 to get the second table. So 0 minus 2. Very good. 1 minus 2. -1. 4 minus 2. 2. Very good. 9 minus 2. And 16 minus 2. Alrighty, very good. And your y values will remain the same, as Jacob mentioned. Are you with me so far? If you're not, stop me right here and ask me a question because I don't want to move.
So we don't actually have to solve the equation and then like plug in the 1, 2.
You can, you definitely can, but that takes longer. But in this way, if you understand that, hey, my graph is moving 2 units to the left, which means all my x values are moving 2 units to the left, then you're just subtracting your x from the original table by 2. And that saves you time.
Now that we're doing,
Rather than actually solve, so we're dissecting what we're actually.
Going step by step, yeah. I mean, you can start from the original points and calculate it backwards, and it will work. So if you started with, again, 0, 1, 4, 9, and 16, you can put that in for your square root of x plus 2 and then work backwards to get your points. Yeah.
So now for the reflecting, the stretching, and the shrinking, do we keep that x plus 2?
Yes, so now you've already moved it to the left, so you have to keep that. And then you can bring in either the shrinking or the reflection. So since they're at the same level, what do you want to do first? Shrinking? Okay, so the shrinking, and that's coming from y equals 1/2 square root of x plus 2. Okay, I think I'm going to move him a little bit to the left.
You don't bring the negative with it?
We're going to do that as a separate step.
That's
Because that's reflection, so we're going to, but if you bring it at the same time, you can basically shrink it and reflect it if you want to, yeah. But I just figured we'd do it separately. So that's our shrinking. So you're doing 1/2 in front of that square root of x plus 2. Will that change our x values? No. Because the 1/2 is on that entire after, yeah. So your x values will actually now stay the same. Your x values are not changing, so they will be your -2, -1, 2, 7, and 14. All the y values from that second table are going to be multiplied by 1/2.
I got a question.
Sure.
What makes us decide that we're using -2, -1, 2, 7, 14 rather than 0, 1, 4, 9, 16?
Oh, because this is where your graph moved 2 units to the left. So from all of these x values, we subtracted 2.
Okay. And now since we subtracted 2, now we're cutting it in half.
Now we're cutting it in half because of that shrink, which is going to actually happen on the y values because it's y equals 1/2 of this, and this is what we have already, right? We already have the value for square root of x plus 2. So you're just taking all of these y values and multiplying by 1/2.
And that's just because the order of what we have to solve it, right?
Exactly.
In order to get there, we have to understand what x is 2.
Right, right, very good. Okay, so for our third column, what are your y values going to be? What is 0 times 1/2? 0. It's okay. 1 times 1/2. Very nice. 2 times 1/2. Good. 3 times 1/2. Yeah, very good. Or 3/2. Sorry, 4 divided by 4 times 1.5. Yeah. No. The y values, not the x values. You're taking the y values and dividing by 2 or multiplying by 1. Okay. Only the first time your x values change because we subtracted by 2, right? Because this here represents our ramp moving 2 units to the left. So that's why your x values change. At this point forward, your x values are not going to change for any of these other transformations. Because all of these other transformations are happening on the y and not the x. The only time transformations happens on the x is if you either move to the right or the left. For the rest of them, all those transformations actually affect your y coordinate. So when you do the 1/2 multiplied by square root of x plus 2, you're taking all of these y values from the second table and multiplying each of these numbers by 1/2, or basically dividing by 2. So 0 times anything is 0, 1 times 1/2 is 1/2, 2 times 1/2 or 2 divided by 2 is 1, 3 divided by 2 is 3/2 or 1.5, 4 divided by 2 is 2. This next table here is going to be our reflection. So this is where you are basically just bringing a negative sign in front of the 1/2 square root of x plus 2. Again, all your x values will stay the same. They have not changed since table 2. Yeah. And what will bringing that negative sign do to your y column here? Yeah, all your signs will change, right? So positives become negative, negatives will become positive, which in this case, they are all positive. So you have negative 1/2, negative 1, negative 3/2, negative 2. So take the y values from the third table and make all of them the opposite sign. Change the sign. Now, what's the last transformation we have to talk about? The k value. Very nice. Yeah, so this is where we're bringing in the entire function now. So that's negative 1/2 square root of x plus 2. We've got this so far. And then the very last thing is add 4.
Or just add 4 to the y values?
Very nice. So x will stay the same. Take all of these y values from your fourth table and add 4 to it to get this last column. So again, these guys stay the same, negative 2, negative 1, 2, 7, and 14. And then you're adding 4 to get that last y column. So 0 plus 4, good. Negative 1/2 plus 4, 3.5, very good. So as a fraction, that's 7/2, or you can write it as 3.5. Negative 1 plus 4, 3. Negative 3/2 plus 4.
Wouldn't it be 1/2, not 3/2?
What do you mean?
The negative, wouldn't it be negative 1/2?
I mean, it's negative 1.5. Yeah, it's 1.5. But this is negative 3/2, which is just a fraction, right? Which is same as negative 1.5 or 1.5, but just as a fraction. So yeah, 4 minus 1.5 gives you 2.5, and that will actually be a positive number. So 2.5 either as a fraction is 5/2 or 2.5, and negative 2 plus 4, 2. Now graphing this will be very, very interesting. Okay, so we are actually going to try and graph each transformation to show how the graph goes from that basic square root of x function with the horizontal translation, the shrinking, the reflection, and then the upward movement, how it's going to change. So be very careful. Each individual table has to be graphed. Yeah, I know. So let's open up a new page here. Can I get that? I won't be able to get him in. Okay. And make sure you are labeling each one of your graphs. So we're starting out with our base function. We moved it 2 units to the left. So negative 2, 0, negative 1, 1, 2, 2, 7, 3. Oh. Okay, so that was moving our graph 2 units to the left. Now comes the shrinking. So that was at 0, 0, but this guy should be 1/2 here. 2 and 1. 7 and 1.5. So basically a good way to know if you've got the shrink, you're shrinking it by 1/2, right? So the distance between the green graph and the x-axis should basically be cut in half by this shrinking graph. So you should be exactly halfway between that green graph and your x-axis, because that's by how much we shrunk our graph, right? And then we did the reflection next. That would make all of these points negative, so this should become negative 1/2. What were you? 2, -1. And then 7 would be at -1.5. Oh, Lordy. Okay, so that should be your reflection mix. And then the final function was where we moved all of these points 4 units up. Okay, so you should be starting at -2, 1, 2, 3, 4, +4. -1 at 3.5. Two and +3. 7 and 2.5. Oh, I don't know about this guy. Yeah, I know. By the time you get to this, you have a jumbled mess in there.
We get any thoughts of colors on that?
No, colored pencils or pens definitely work better. If you make a lot of mistakes, colored pencils. Or just label your graph. But yeah, this guy ends up being a big jumbled mess because you have every possible transformation in there, right? If it was just horizontal and vertical, that's 3 graphs. You will have something like this, yes, on the test. What do you mean all of them? Something like this, yeah, yeah, where you have all the transformations in, yeah. Okay, so I do want to actually show you this guy on our graph so we can get a better picture of what this should look like instead of the hot holy mess we have in there. All right, so that's our base function, square root of x. We moved it 2 units, whoa, to the left, right? Then we did 1/2 square root, no, bless you, go down, go back down. Oh, come on, square root of x plus 2, so that's our shrinking, right? So again, we started out with the blue as the base function, the green is moving it 2 units to the left, and then the purple is shrinking it by 1/2, and again, you can see that distance between the x-axis and the green gets cut in 1/2. Then we did a reflection. Will he let me select all that? Oh, yes. No, there we go. Okay, reflection. And then the very last part is where we move it 4 units up. Oh, come on. Okay. 4 units up. And then if we take all of these out, so this is the reflection, the shrinking, and moving it to the left. So that's your original function that you started out with. And by the time you were done with it, that's what it ends up looking like. So it's skinnier, 2 units to the left, 4 units up, and of course, you're seeing that it's been reflected as well. Okay, so that order is something that you really have to be careful about. So horizontal first, vertical at the very end, right? So start with horizontal, wait till the end to do the vertical, and in the middle, at the same level, you can do reflection first, you can do stretching first, you can do shrinking first, doesn't matter. As long as horizontal is the first thing you do and vertical is the last thing you do. The rest 3 of them are going to be
So
in the
really-
middle. Just one second.
We have to graph every single one or just the thing?
So I usually prefer that you show me the transformation with the tables, but graph the final graph. But what's been happening is you guys are not showing me the transformation with the tables until you end up losing points. So I think the best thing would be to do everything, to do the tables and do the transformations on the test. So show me step by step, and that's the best way, because in the past I've done only tables and then show me the final graph, but most of you don't do the table, then you end up losing a big chunk of your points for that problem. Okay, so do what we did for this example in class is do the tables, but then show every transformation also like we did. Okay? But please make sure you are labeling each graph so that you know which graph represents which transformation. Okay? Alrighty, so if we had to talk about the final function, let's get rid of that base function also. Think about it and tell me what is your domain and range going to be for the final function. And you actually have room here, which is kind of hidden in this jumbled mess, but it's actually for domain and range right here. So that's going to be our final function, which is in purple. Which is for this function here. So look at the x values. Where is your function on the x-axis? Sorry?
-2?
To where?
Oh, negative. Then go positive.
Yeah, so you are starting at -2. Again, remember, that's the graph in the purple, our final graph. You are starting at -2 and you're only going to the right, which means you are headed towards positive infinity. Very good. So your domain bracket -2 to positive infinity. Again, same thing. Think about it. What's the range? Negative infinity to positive, so Jacob?
0?
Yeah.
Is that 0?
You're looking for the final function,
That's the blue one, right?
the purple.
Oh.
Well, whatever color it looks like to you. But yeah, that final one that we did. Or you can look at it from this side here. So this arm, of course, is going down, right? Because we reflected it, which means this arm will be heading towards negative infinity at the bottom. And at the maximum, it goes to y equals 4. So yeah, again, negative infinity and then stopping at 4. All right, very good, guys. So negative infinity to positive 4. So 0 would be with the original function, but now that it's been moved and broken up into so many pieces that it's completely changed from where it started out at. Question on this, guy? So I know it's a pretty tedious process going through those transformations, but if you can understand these steps, then you know a lot of this section is going to become easier for you. Any questions?
When,
Go ahead.
no, I just saw it was negative.
Oh, okay. All righty. Okay, so that takes us to the last part here, which is talking about the linear family of functions. And that means the base function will be just your y equals x or f of x equals x function, you know, that straight line with a slope of 1. So it's called the identity function because you set it up as y equals x. So whatever is your x value is going to be your y value, right? So that's why it's called the identity function. It goes through the origin of 0, 0 with a slope of 1. So the idea is, how does this transformation affect the linear family of functions, you can actually clean it up. So if you have A, which will give you your stretching or shrinking, if you put a negative on it, it becomes reflection. The H gives you your horizontal transformation, K gives you the vertical transformation. So you can see with this little calculation here that we have, you can actually write it from the transformation format into just a slope intercept, because start by taking this A value and distributing it with the X minus H, so that becomes A times X minus A times H, and you're just bringing the K down. Now X is your variable, but H is just a number, which means I can actually add this negative AH plus K together, and this whole thing is actually going to end up becoming just one single number, and we can call that as B. And the AX, replace that A with an M. So this guy here becomes MX. This whole part here becomes your B. So each linear equation that you look at is actually a transformation on that original linear y equals x function. So every time you have 3x minus 4, y equals 3x minus 4, that's a transformation. Y equals negative 1/2 x plus 2, that's a transformation on your linear function. So they actually have this linear function here, y equals negative 2x plus 5, and they're asking us to graph this using transformation. So we actually are not going to do the entire thing here. You have negative, which is giving us reflection. You have the 2x, so the 2 is giving us stretch or shrink? Stretch, because it's greater than 1, right? And then the, what is it, plus 5 will give you the vertical movement. So you've got the negative, which is your reflection.
Wouldn't the negative be your slope?
Technically for a line, that's your slope, yeah. But since they're asking us to use transformations, we're not going to be using the slope formula to help us out here. We're going to do this with, that's your stretch, and that's your K equals 5, which means you're moving upwards. Okay. I'm actually going to switch over to our notebook here. And you've got y equals negative 2x plus 5. So again, you can use those standard 5 points, and since this is y equals x, an identity function, those values will still stay the same. You can do 2x next as your stretching, keeping the same x values. How will your y values change? Yes? Wider. You're talking about it getting flatter, it should not. Because it's 2x, right? So that 2, yeah, it should make it steeper. So this one actually multiply every x value by 2 since you're doing 2x. So you'll get negative 2 times 2. So that will be negative 4. Negative 1 times 2. 0 times 2, of course, will be 0. And then 1 times 2. And then 2 times 2. So each y value will basically be multiplied by 2.
You want us to break down each, for every problem that we do now, you want us to break down each step?
Whenever they say using transformations, yes. Yeah, so that's what that instruction basically is telling you. Then our next part will be reflection. Again, we have made no change to our x values at all. With that reflection, what's going to happen to your y values?
Opposite signs, isn't it?
Very nice. Yeah, so positives become negatives. negatives become positives. And then your very last one is where we do the vertical translation, which is going to be your plus 5. So take all the values from here and add 5 to it. X values will still stay the same. They haven't changed. Okay, so again, from the very last column of y, add 5 to it. What are you going to get?
3, 4, 5, 6, 7.
You're adding 4 plus 5, right? Because we've got 4 here. So you're adding 4 plus 5, right? To the y values. I think you did x. Yeah. So 4 plus 5 would be 9. 2 plus 5? 7. So that would be 12. 0 plus 5 would be 5. Negative 2 plus 5? Negative 4 plus 5? There you go. And then we can do our graph based on that. And you know what? Just do your original and the final. Don't do the intermediate steps because I think at this point you guys know what you're doing. So just the base function and then the final function.
-2, -2.
The y equals x function and then the negative 2x plus 5. If you want to do all of them, you're definitely welcome to do all of them. So my base function would be 0, 0, 1, 1, 2, 2, negative 1, negative 2, negative 2. So just your positive slope of 1. And then my final graph is negative 2, positive 9. I don't think I have that point. Negative 1, 7. Okay. Negative 1, 7, 0 and 5. 1 and 3. 2 and 1. Where would I be crossing the x-axis?
X-axis.
2.5, right? Would actually be crossing halfway right there between 2 and 3. How can I find that point? And you guys did this kind of question on the last exam.
No, I'm doing a whole different thing.
Okay. No, this is where you would just take your y value, set it equal to 0, and then calculate backwards to find x. So you should get 5 halves, 2.5. Okay. All right, so this is what I'm asking. If you want to do the intermediate steps, you can, but you should see that with that negative sign, we had a reflection. So instead of having now a positive slope, our line has a negative slope, right? And then you can see how this original line had a slope of 1, but this guy now has a slope of, 2x, which means it's going to be a steeper slope. So this line should be steeper than this guy. And then since we did that plus 5, you are now crossing, instead of at 0, 0, you're crossing at positive 5 on the y-axis. But if you were normally graphing this, you would have used 0, 5 as your y-intercept and then used your slope, right? Rise over run to help you come up with this. With transformation, it just ends up looking a little bit different. Domain and range for that final function. The one in green, our very final function. For domain, okay, and range. Yeah, because it's a straight line. And it's with a negative slope, so you will be going to both positive and negative infinity. Okay, questions on number 9? All right, so that's as far as transformation goes. Now, of course, you will see the remaining part of it. We're getting into discussions of symmetry and stuff like that. So we'll pick up from there next time. Now, before you guys leave, I do want to give you your handouts.